The OSIRIS-REx mission. When NASA launched the OSIRIS-REx spacecraft in September 2016, scientists expected to collect samples from a distant asteroid and return them to Earth. What they didn't expect was to discover something so unusual that it would fundamentally challenge our understanding of how our solar system formed. The origins, spectral interpretation, resource identification, security regolith explorer, OSIRIS-REx for short, represents one of the most ambitious space missions ever attempted. Unlike previous flyby missions, OSIRIS-REx was designed to physically touch down on an asteroid, collect pristine samples, and bring them back to Earth uncontaminated. The mission had three main objectives: return at least 60 grams of material, map Bennu in unprecedented detail, and measure the Yarkovsky effect, a subtle force that causes asteroids to drift from their expected orbits. Why spend over $1 billion in 7 years on this mission? Because Bennu is a cosmic time capsule. Asteroids like Bennu are leftover building blocks from over 4.5 billion years ago, preserving materials from when our solar system formed. By studying these ancient rocks, scientists hope to understand how planets formed and how organic compounds necessary for life arrived on Earth. After launching from Cape Canaveral, OSIRIS-REx traveled over 1.2 billion miles before reaching Bennu in December 2018. The spacecraft carried sophisticated cameras, spectrometers, and a laser altimeter. The most critical component was TAGSAM, the touch-and-go sample acquisition mechanism, a robotic arm designed to briefly contact Bennu's surface and collect samples using nitrogen gas. What is Bennu? Bennu is a near-Earth asteroid that passes close to our planet every 6 years. Discovered in 1999, it's officially designated 10-19955 Bennu, named after an ancient Egyptian mythological bird associated with creation and rebirth. Bennu measures approximately 490 meters in diameter, about the height of the Empire State Building. Despite having a mass of 73 million metric tons, its overall density is surprisingly low at only 1.2 grams per cubic centimeter. This low density hinted that Bennu's structure might be very different from expected. Bennu is classified as a B-type carbonaceous asteroid, among the most primitive objects in our solar system. These asteroids have changed very little since formation, essentially cosmic fossils preserving conditions from over 4.5 billion years ago. Observations from Earth revealed that Bennu contains hydrated minerals, minerals with water molecules bound within their structure. This suggests asteroids like Bennu could have delivered water to early Earth. The presence of carbon-rich compounds raised questions about whether asteroids delivered the organic building blocks necessary for life. Bennu's orbit brings it close to Earth regularly. Current calculations show a 1 in 2,700 probability of Earth impact sometime between 2175 and 2199. While small, these odds make Bennu one of the most potentially hazardous known asteroids. Understanding its composition could be crucial for developing deflection strategies. The asteroid rotates every 4.3 hours and has a distinctive spinning top shape with an equatorial bulge and flatter poles. This shape results from rotation, gradually redistributing material from poles to equator over millions of years. Scientists classify Bennu as a rubble-pile asteroid, not solid rock, but a loose collection of boulders, rocks, and dust held together by gravity. This structure likely formed when a much larger parent asteroid, perhaps 100 kilometers across, shattered in a catastrophic collision. The fragments gradually reassembled under mutual gravitational attraction. Before OSIRIS-REx arrived, scientists predicted a relatively smooth surface with abundant fine-grained regolith. These predictions turned out to be dramatically wrong. Landing difficulties. When OSIRIS-REx approached Bennu in December 2018 and began detailed surveys, mission scientists experienced collective shock. The asteroid bore almost no resemblance to the smooth world they predicted. Instead of vast plains of fine regolith, Bennu's surface was jagged, rough, and absolutely littered with boulders. Mission planners expected numerous safe landing sites at least 25 meters in radius. They found exactly 0 sites meeting their original criteria. This sent the team into emergency planning mode. Years of procedures based on assumptions about Bennu's surface were now proven false. The largest safe area available was barely 20 meters across, about the size of a few parking spaces. Principal investigator Dante Loretta described seeing Bennu's true surface as both terrifying and exhilarating. Engineers ran new simulations while software developers modified the spacecraft's autonomous navigation systems to handle tighter tolerances. But challenges didn't end with boulders. As OSIRIS-REx conducted orbital surveys, scientists noticed something extraordinary. Bennu was active. Small particles regularly ejected from the surface, shooting into space like miniature volcanic eruptions. This discovery was unprecedented. While comets eject material as their ices sublimate, asteroids, especially small ones like Bennu, were thought to be inert, dead rocks. Yet between December 2018 and February 2019, cameras documented 11 distinct particle ejection events, with some ejecting hundreds of particles at velocities up to several meters per second. Scientists proposed several theories: meteoroid impacts, thermal fracturing from temperature swings, or trapped water vapor release. Each had merit, but determining the cause required more analysis. The team also discovered Bennu's gravitational field was more complex than expected. Density variations created a lumpy gravitational field, complicating orbital mechanics. Another surprise was widespread hydrated minerals across Bennu's surface. The abundance and distribution surprised scientists. They also discovered bright carbonate veins, minerals forming from carbonic acid interaction with rocks in water, crisscrossing surface rocks. Despite challenges, the team identified 4 potential collection sites named after birds: nightingale, kingfisher, osprey, and sandpiper. They selected Nightingale, a small northern crater, as the primary target. Though far more confined than planned, Nightingale showed signs of fine-grained material easier to collect. Touchdown on Bennu, October 20th, 2020, marked one of NASA's most nerve-wracking days. After years of planning and countless simulations, OSIRIS-REx was ready to attempt sample collection. The entire approach was autonomous. Due to 18.5-minute light travel time between Earth and Bennu, mission controllers couldn't operate in real time. The spacecraft had to navigate to a spot just 8 meters in diameter while avoiding boulders. The descent took approximately 4.5 hours. As OSIRIS-REx descended, TAGSAM extended to its full 3.35-meter length. At the end was a 30-centimeter circular collector head that would briefly contact Bennu's surface. Upon contact, compressed nitrogen gas would fire, stirring up surface material for capture. The entire contact would last just 5 to 6 seconds. Touchdown occurred exactly as planned at 6:11 p.m. EDT. What happened next shocked everyone. Instead of resting on firm surface, TAGSAM sank deep into Bennu's regolith. Images showed the collector head penetrating several centimeters into extremely loose, fluffy material with almost no resistance. It was like pushing into a ball pit rather than solid ground. The surface material had virtually no cohesion, offering less resistance than freshly fallen snow. This discovery completely upended understanding of asteroid surfaces. The material was so loosely packed it had density even lower than Bennu's already low average. Scientists described it as having structure similar to popcorn. individual grains barely touching with vast empty space between. 2 days later, OSIRIS-REx performed a special maneuver to estimate collected mass. Engineers calculated TAGSAM had collected approximately 250 grams, more than 4 times the mission requirement and the largest asteroid sample ever collected. However, there was a problem. Images revealed material escaping. The abundance of collected material, combined with small rocks lodged in the sealing mechanism, prevented the flap from closing completely. Scientists could literally see particles slowly leaking into space. This triggered emergency response. The team immediately accelerated stowing plans. On October 27, 2020, just 7 days after collection, the TAGSAM head was successfully inserted into the sample return capsule and sealed. While some material was lost, well over 100 grams remained, still far exceeding requirements. Return to Earth. With precious samples secured, OSIRIS-REx began preparing for the long journey back. On May 10, 2021, the spacecraft fired main thrusters for 7 minutes, breaking free of Bennu's orbit and beginning a 1.4 billion-mile journey taking over 2 years. September 24, 2023 was landing day. The target was Utah Test and Training Range, a military facility in western Utah's desert. 4 hours before atmospheric entry, OSIRIS-REx released the sample return capsule. The capsule hit Earth's atmosphere at 8:42 a.m. MDT, traveling over 27,000 miles per hour, faster than any human-made object had ever entered Earth's atmosphere. The heat shield glowed white-hot, as friction created temperatures exceeding 5,000 degrees Fahrenheit. At approximately 20,000 feet, a drogue parachute deployed to stabilize the capsule. At 10,000 feet, the main parachute deployed, a brilliant orange and white canopy, 24 feet in diameter. The capsule touched down at 8:52 a.m. MDT. A recovery team converged within minutes. The capsule was placed in a clean container and transported via helicopter to a temporary cleanroom facility, then flown to NASA's Johnson Space Center in Houston, opening the sample. At Johnson Space Center, a specialized cleanroom facility maintained an ultra-pure nitrogen atmosphere to prevent contamination. On September 26, 2023, scientists began opening the return capsule. Even before accessing the main sample, they made an exciting discovery. Dark dust and small rock fragments coated parts of the canister lid. This bonus sample had leaked from TAGSAM during the journey home. Fully disassembling the TAGSAM head took weeks. As the collection chamber opened, scientists gasped. It was packed with material, far more than expected. Large rocks, small pebbles, and fine dust filled every available space. Total collected mass was eventually confirmed at approximately 121.6 grams, double the mission requirement even after accounting for leakage. But it wasn't just quantity that amazed scientists, it was diversity. Samples showed incredible range of colors, textures, and compositions. Some particles were jet black and carbon-rich. Others were lighter with visible mineral grains. Some rocks showed brecciation, where multiple rock types had been smashed together and fused by ancient impacts. Under electron microscopy, samples revealed even more complexity. One particularly exciting aspect was extreme fragility. Many particles were so delicate they could barely support their own weight under Earth's gravity. These were materials never subjected to Earth's compacting forces, preserved in pristine, fluffy structure for billions of years. The curation team carefully divided samples into portions for different analyses. Critically, at least 75% of total sample was placed in long-term archival storage, preserved for future generations of scientists with techniques not yet invented. Pre-solar grains. Among many exciting discoveries, perhaps none captured scientific imagination more than detection of pre-solar grains. These are literally the most ancient materials humans have ever held. Grains that formed in dying stars' atmospheres, billions of years before our solar system existed. Pre-solar grains are identifiable by distinctive isotopic signatures. Every star produces elements through nuclear fusion, but specific isotope ratios depend on the star's mass, temperature, composition, and evolutionary stage. These isotopic fingerprints are so distinctive, scientists can determine not just that a grain is pre-solar, but specifically what type of star created it. Pre-solar grains found in Bennu samples are extraordinarily rare, making up only a few parts per million. Despite rarity, they're scientifically invaluable. These grains represent actual stardust, formed in stellar environments and ejected into interstellar space, where they drifted for millions or billions of years before being incorporated into material that eventually formed our solar system. Types of pre-solar grains found include silicon carbide crystals, graphite particles, and various oxide minerals. Each type tells a story about its stellar origin. By analyzing multiple isotopes within individual grains, scientists can reconstruct nuclear processes that occurred in stars where these materials formed. What makes pre-solar grains in Bennu particularly valuable is pristine preservation. On Earth, most rocks have been heated, subjected to tectonic forces, and chemically altered over billions of years. But, locked within asteroid Bennu, preserved in space's vacuum at cold temperatures, these grains have remained virtually unchanged since before the Sun existed. Some pre-solar grains may have origins in supernovae, explosive deaths of massive stars. These catastrophic events produce unique isotopes through rapid nuclear reactions that can't occur in normal stellar environments. What they found on Bennu. Comprehensive analysis of Bennu samples has revealed discoveries fundamentally changing our understanding of asteroids, the early solar system, and origins of Earth's water and organic compounds. One of the most important discoveries is confirmation of abundant water-bearing minerals throughout samples. Many rocks from Bennu contain up to 10% water by weight, locked into hydrated minerals like clays and carbonates. This water is chemically bound within mineral structures, proving substantial water interacted with Bennu's parent asteroid in the past. Specific types of hydrated minerals provide clues about conditions under which water interaction occurred. Scientists identified serpentine minerals, which form when water reacts with iron and magnesium-rich rocks at relatively low temperatures. They also found carbonates, which form when carbon dioxide dissolves in water and reacts with rocks. Temperature estimates based on mineral compositions suggest aqueous alteration occurred at temperatures between 50 and 150 degrees Celsius, warm but not extremely hot. These are temperatures that could be maintained by radioactive heating in a large asteroid's interior during the first few million years after formation. But the water story gets more interesting. Stable isotope analysis of hydrogen in water-bearing minerals shows isotopic composition closely matches Earth's oceans. This is strong evidence supporting the hypothesis that asteroids like Bennu delivered much of Earth's water during late stages of planetary formation. Beyond water, samples contain remarkable diversity of organic compounds, carbon-bearing molecules including amino acids, the building blocks of proteins. Scientists identified dozens of different amino acids in Bennu samples, including many commonly found in living organisms on Earth, but also many that are not. The presence of both biological and non-biological amino acids proves chemical building blocks of life can form naturally in asteroids. Other organic compounds detected include polycyclic aromatic hydrocarbons, PAHs, alcohols, carboxylic acids, and various other complex carbon-bearing molecules. The diversity is staggering, essentially a library of prebiotic chemistry, showing kinds of molecules available when life began on Earth. The physical structure of Bennu's materials has proven equally fascinating. Detailed analysis revealed some samples have porosity exceeding 50%, meaning more than half their volume is empty space. These materials are held together by van der Waals forces and perhaps static electricity, but have virtually no structural strength. This extreme fragility and porosity have important implications. They suggest Bennu and similar asteroids are much more vulnerable to disruption than previously thought. This affects how we think about asteroid evolution, the asteroid belt's collision history, and even strategies for potentially deflecting hazardous asteroids. Mineralogical analysis identified complex mixture of materials. Dominant minerals are phyllosilicates, sheet-like clay minerals forming from alteration of other minerals by water, but samples also contain magnetite, sulfides, carbonates, and various silicate minerals including olivine and pyroxene. Scientists discovered calcium-aluminum-rich inclusions, CAIs, materials thought to be among the very first solids to condense from the hot solar nebula. These inclusions are effectively the oldest materials in our solar system, dating back 4.567 billion years. Samples also revealed evidence of space weathering, gradual alteration of surface materials by micrometeorite impacts, solar wind bombardment, and cosmic ray exposure. Dark, impact-melted glass coats some particles, while others show tracks from high-energy cosmic rays passing through them. Chemical analysis revealed Bennu's composition closely matches a rare class of meteorites called CI chondrites. These meteorites are considered the most primitive, ones whose composition most closely matches the Sun's composition. Only 5 CI chondrites have ever been recovered on Earth, all heavily contaminated by terrestrial weathering. Bennu samples effectively provide pristine CI chondrite material for the first time. Bennu's past. By synthesizing all data from orbital observations, surface measurements, and detailed laboratory analysis, scientists have reconstructed a detailed history of asteroid Bennu spanning billions of years. The story begins 4.567 billion years ago in a disk of gas and dust, swirling around the newly formed Sun. In this solar nebula, first solid materials were condensing from vapor, tiny grains that would become building blocks of planets and asteroids. Within perhaps 2 to 3 million years of the solar system's formation, a substantial parent asteroid had formed, possibly 100 kilometers or more in diameter. This parent body was large enough that radioactive decay generated significant internal heat. The interior warmed up, melting ice and creating liquid water that flowed through fractures and pores in rock. This aqueous alteration phase lasted several million years. Liquid water chemically reacted with minerals, transforming them into clays, serpentines, and carbonates. Water also facilitated organic chemistry, allowing simple carbon compounds to react and form more complex molecules. Eventually, radioactive heat sources decayed and the parent asteroid cooled. Liquid water either froze or was incorporated into hydrated minerals. Then, perhaps 700 million to 1 billion years ago, catastrophe struck. The parent asteroid was hit by another asteroid in a catastrophic impact that completely shattered the parent body, reducing it to countless fragments. In the aftermath, gravity began reassembling fragments. Slowly, over perhaps thousands or millions of years, pieces came back together under mutual gravitational attraction. This reassembly wasn't neat or organized. Fragments collided and stuck together haphazardly, creating a loose rubble pile rather than solid body. This is how Bennu formed. Once Bennu coalesced, it didn't remain undisturbed. Over hundreds of millions of years, the asteroid experienced numerous smaller impacts. Space weathering processes gradually altered Bennu's surface. Solar wind particles bombarded the surface, causing chemical changes. Micrometeorite impacts melted tiny patches of rock. Cosmic rays passed through Bennu, leaving tracks in mineral grains. At some point, Bennu's orbit was perturbed by gravitational interactions, sending it from the main asteroid belt into a near-Earth orbit. This transition likely occurred within the last several million years. Today, Bennu continues its journey around the Sun, regularly crossing Earth's orbit. Next stop for OSIRIS-REx. When OSIRIS-REx released its sample capsule toward Earth on September 24, 2023, the spacecraft itself was far from finished. Rather than being decommissioned, it was directed onto a new trajectory for an extended mission under a new name, OSIRIS-APEX, Apophis Explorer. The target is Asteroid 99942 Apophis, one of the most infamous near-Earth asteroids. Discovered in 2004, Apophis initially caused considerable concern when calculations suggested possible Earth impact in 2029. Further observations ruled out that particular close approach as hazardous, but confirmed Apophis will make an extraordinarily close pass of Earth on April 13, 2029. During this 2029 encounter, Apophis will pass within approximately 31,000 kilometers of Earth's surface, closer than many geostationary satellites. This is one of the closest approaches of an asteroid of Apophis's size, approximately 370 meters in diameter, that will occur during the current century. OSIRIS-APEX will arrive at Apophis well before the close Earth encounter, allowing observation of the asteroid before, during, and after its interaction with Earth's gravitational field. Earth's gravity will substantially affect Apophis during the flyby. Tidal forces may trigger landslides, cause surface changes, or even alter the asteroid's rotation state. The mission plan calls for OSIRIS-APEX to conduct detailed observations of Apophis's surface, mapping it in high resolution similar to what was done at Bennu. Scientists want to understand how Apophis is similar to or different from Bennu. One particularly exciting planned activity is a close approach maneuver where OSIRIS-APEX will descend toward Apophis's surface and fire its thrusters while hovering above it. The exhaust from thrusters will blow away surface dust and loose material, exposing subsurface materials that haven't been weathered by space exposure. OSIRIS-APEX won't attempt to collect samples from Apophis. It no longer has a sample collection mechanism. But observations will be valuable for understanding Apophis's structure and composition, important for planetary defense. The spacecraft will spend multiple years traveling to Apophis, arriving in early 2029, just months before the close Earth encounter. The OSIRIS-APEX mission will continue through at least mid-2029. Beyond OSIRIS-APEX, the legacy of the OSIRIS-REx mission to Bennu will continue for decades through analysis of returned samples. The samples stored at Johnson Space Center represent an incredible scientific resource that will keep researchers busy for generations. The OSIRIS-REx mission to asteroid Bennu represents one of humanity's greatest achievements in space exploration. From its launch in 2016, through successful return of samples in 2023, and its ongoing extended mission as OSIRIS-APEX, the mission has exceeded expectations at every turn. The discoveries made at Bennu have fundamentally changed our understanding of asteroids. Rather than dead, inert rocks, we now know even small asteroids can be dynamic, active worlds with complex histories. The extreme fragility and low density of Bennu's surface challenges our assumptions about asteroid structure and has important implications for planetary defense strategies. The returned samples are a gift that will keep giving for decades or centuries. They provide pristine material from the early solar system, containing pre-solar grains older than the sun, organic compounds that may have seeded life on Earth, and water-bearing minerals that tell stories of ancient, aqueous environments in the asteroid belt. Perhaps the Bennu samples connect us directly to our cosmic origins. The water in Earth's oceans, the carbon in our bodies, the very elements that make up our planet, all were delivered by objects like Bennu in the chaotic early days of the solar system. The strange substance discovered on Bennu, those oddly loose, barely cohesive materials that confounded expectations, opened a window into asteroid physics we didn't know existed. It revealed our understanding of how small bodies in the solar system work was incomplete. The success of OSIRIS-REx demonstrates what's possible when human ingenuity, advanced technology, and scientific curiosity combine. It shows we can reach out across vast distances of space, touch ancient worlds, and bring pieces of them back to Earth for study. The strange substances, unexpected discoveries, and scientific revelations from asteroid Bennu remind us that the universe is full of surprises waiting to be uncovered. Each answer opens new questions, and each discovery inspires new missions. The story of OSIRIS-REx and Bennu is just one chapter in humanity's ongoing journey to understand the solar system. If you're new here, welcome. If this episode helps you understand the universe better, please like the video and subscribe for more cosmic discoveries.